Gravimetric stoichiometry is a big word, but it means something that's actually quite simple. It's the way that we figure out the mass of reactants or products using mole ratios. And we've been looking at mole ratios already, and we get the mole ratios from balanced chemical equations. So this is very useful in any type of manufacturing process, making cars to baking cakes. We use it all the time in chemistry when we're figuring out how to make solutions, how much mass to use in a reaction. It's very important to know how much raw material is needed to make a specific amount of product. That way, we don't waste anything. We don't overuse too much chemical. We don't use too much energy. So you're going to use this math many times in this course. So the first step is you must have a balanced chemical equation. So if you have a chemical equation for your reaction, double check, make sure it's balanced. Put in the amounts that you know underneath that species in the equation. That includes molar masses. So that includes your molar masses for your substances. Then you're going to convert into moles for the items you know. And then we're going to use the mole ratio from the balanced chemical equation to predict the amount of moles of the desired substance. Then we're going to convert our moles to mass using molar mass. So here's a flow chart that actually describes what we're doing. And this is a common type of problem in college and university. You're given information about substance A over here. You're given the mass of substance A, and you convert it into moles of substance A over here. And you do that using this formula. Moles is equal to mass divided by molar mass. Once you have the moles of substance A, you can use your mole ratio to convert into moles of substance B. Once you have moles of substance B, you can calculate the mass of substance B using your molar mass of substance B. And that's basically all you do. Calculate your moles, convert them to moles of the other substance, then convert the moles into mass. Okay, so here's our first problem. Carbon dioxide is produced by astronauts and can be removed with lithium hydroxide. The reaction produces lithium carbonate and water. An astronaut produces an average of 1,000 grams of CO2 per day. What amount or what mass of lithium hydroxide should engineers put on board a spacecraft per astronaut per day? So this is kind of crucial that you know how to do this type of reaction, because you can't just, here you go, here's some more lithium hydroxide if you get the amount wrong, because they're up in space. So, carbon dioxide is produced by astronauts, can be removed with lithium hydroxide. So we know there's the reaction. The reaction produces lithium carbonate and water. So we can write a balanced chemical equation, and we know we've got this mass of carbon dioxide per day. We're looking for lithium hydroxide. So steps 1 and 2, we need to write a balanced chemical equation and put the information that we know underneath the substances. So here's the chemical equation, but it's not balanced. So we need 2 lithium hydroxides and everything else, 2 lithiums, 3, 4 oxygens, 3 and 4 oxygens. This is balanced. Okay, so now write in what we know. We know the mass of carbon dioxide. We want to find the mass of lithium hydroxide. So now we have to calculate the molar mass of carbon dioxide so that we can calculate the moles of carbon dioxide. So the molar mass of carbon dioxide is 44.01 grams per mole. So here's the 2 ways to write out the moles of carbon dioxide. You can either do formulas, so N is equal to mass divided by molar mass. Sorry, that got crooked. Or dimensional analysis. So, either way, we can figure out that the number of moles of carbon dioxide is 22.72 moles, whether we use formulas or dimensional analysis. So we have 22 moles of CO2, so we need to multiply this by the mole ratio. We want to get rid of carbon dioxide, so it goes on the bottom. And we want mass of lithium hydroxide, so it goes on the top. And our mole ratio from our balanced chemical equation. So these are the coefficients. Is 2 to 1. So now the moles of carbon dioxide are converted to moles of lithium hydroxide, and we have double the number of moles. We need 45.44 moles of lithium hydroxide. Step 5, we have to convert that moles into mass. So we've converted from mass to moles, converted our moles, now we're going to convert to mass. So we need the molar mass of lithium hydroxide, so 23.94 grams per mole. So if we take the number of moles that we have of lithium hydroxide and multiply it by the molar mass, we will calculate the mass of lithium hydroxide that we want. Now, we can only have 3 significant digits in our answers, so we round it off. If you want to use dimensional analysis instead of formulas, we want mass of lithium hydroxide. So we use our molar mass times our number of moles, and that will give us the same result. Okay, dimensional analysis can be used in a better way than just at each step though. What we can do is we can use dimensional analysis to solve this entire solution in one line with no intermediate steps and no losing marks for sig fig rounding or dropping of units. We want to find grams of lithium hydroxide. That's what we want. We have grams of carbon dioxide. So what we know is the molar mass of lithium hydroxide is 23.95 grams per mole. Carbon dioxide molar mass is 44.01 grams per mole. And we know we have 1 kilogram or 1,000 grams of carbon dioxide. So, because we want grams of lithium hydroxide, we start with the molar mass of lithium hydroxide. We've got moles on the bottom, we've got to get rid of those. This is moles of lithium hydroxide. So, we need our mole ratio, but lithium hydroxide has to be on the top because we want it to cancel. And the coefficients from our balanced chemical equation are 2 to 1. But now we've got moles of carbon dioxide. We want to get rid of carbon dioxide, so we need the molar mass of carbon dioxide. So now moles of CO2 are gone, but we have grams of CO2. We want to get rid of that, so we use our mass of CO2, and then in the end, because it's on the top and the bottom, our grams of CO2 are gone. So in your calculator, you would take 23.95 times 2 times 1,000 divided by every number on the bottom. So we don't really need to put divide by 1 on the calculator, but the other number on the bottom is 44.01. So you should end up with the same number, 1,090 grams of lithium hydroxide. Okay, example 2. Sometimes a question will ask for the number of molecules, atoms, or formula units. And then you just change the last step. Instead of calculating the mass, you calculate the number of particles. Now that you know moles, this doesn't happen often, but occasionally. Okay, so passing chlorine gas through molten sulfur produces liquid disulfur dichloride. How many molecules of chlorine react to produce 50 grams of disulfur dichloride? So this reaction is giving you information about your products, and you're asked to find something about one of your reactants, which is another a good feature of this, because if you know how much of something you need to make, you can work backwards to figure out how much of each reactant you need to make your product. So we have to start with a balanced chemical equation. So chlorine gas reacts with sulfur to produce disulfur dichloride. So it's a balanced chemical equation. After that, you have to put in what you know underneath the substances that you have information about. So we know we've got 50 grams of disulfur dichloride, and we want to find information about chlorine. So we're going to need to find the molar mass of disulfur dichloride and chlorine gas. So here's the calculation to figure out the molar mass of disulfur dichloride. 2 sulfurs plus 2 chlorines, add them together and you get the molar mass is 135.02 grams per mole. Okay, so I've moved it up so you can see. Alright, so we've got the molar mass. So now we can calculate the number of moles. So we take our mass and we divide by our molar mass. If you're using formulas to find the number of moles. If you like dimensional analysis and you want to do it stepwise, we want moles, so we have to flip over our molar mass. And multiply it by the mass. Oops. Grams cancel. You get the same number, 0.3703 moles. You'll notice that we're keeping one extra significant digit because this is an intermediate calculation. Okay, so now that we have the moles of disulfur dichloride, we have to convert to the moles of chlorine, and to do that we use the mole ratio. So we take the moles of what we know and we convert it to the moles of what we want. So we want chlorine, so our disulfur dichloride goes on the bottom. And we calculate the moles of chlorine. We want the number of molecules of chlorine, so now we need to use Avogadro's number. 6.02 times 10 to the 23. Chlorine is a diatomic element, so its particles or molecule per mole. So we're going to use this number. So if I multiply these two numbers, my moles of chlorine will cancel and I'll be left with molecules of chlorine. Because we have only 3 sig figs in our initial data, we have to have 3 sig figs in our final answer. So 2.3 times 10 to the 23 molecules of chlorine are needed to react to produce 50 grams of disulfur dichloride. Now again, the beauty of dimensional analysis is we can solve this problem on one line, no intermediates, no making mistakes of using of, losing significant digits. We know Avogadro's number. We know the mole ratio, 1 disulfur dichloride for every 1 chlorine. We know the molar mass of disulfur dichloride. And we know we have 50 grams of disulfur dichloride. So the piece that we use first has to contain the units of our final answer, and our final answer wants molecules of Cl2. So we're going to start with Avogadro's number, because molecules are on top. But this has moles of Cl2 on the bottom, so we need to get rid of moles of Cl2. But we know there's 1 mole of Cl2 for every 1 mole of S2Cl2 in our balanced chemical equation. So now we've used our mole ratio. We want chlorine on the top, because chlorine is on the bottom in the first ratio. Now we've got disulfur dichloride. We want to get rid of it, and we need moles, so we use the molar mass. Of S2Cl2. But this gives us grams of S2Cl2 that we want to get rid of, so we're going to multiply it by our 50 grams of S2Cl2. So now that's gone as well. So in our calculator, 6.02 times 10 to the 23rd times 1 times 1 times 50. So that's everything from the top. Divide by 1, divide by 1 for the first two ratios, and then divide by 135.02. So everything on the top is multiplying, everything on the bottom is dividing, and you should get the exact same number. What I want you to do now is I want you to try page 227, questions 1 to 3. But before you get your books open, on the back of this page, I have given you the skeletal chemical equations for the reactions for question 227, 1 to 6, to help you. So I want you to do 1, 2, and 3. Use these skeletal and chemical equations to help start you. You're going from mass to moles of the quantity we don't know but we want, and then we're converting to mass. Good luck. So you're either going to do it the long way using all the formulas and the steps, or choose just to do one line using dimensional analysis.